because it's per like time frame in the episode. So if something does actually come out of the goal region after it entered, it notices that, like it sees that it's actually getting less reward. So it is like that's probably directly contributing to that, but it's reinforcement learning. You can only assume. Well, thank you for the question. That was a good one.
A question to the second speaker. So I really like your work about mapping from one problem to another similar problem. So I'm just curious, like, do you have any formal metric about the similarity between two RL problems?
No, not yet, but we're looking into that. We're looking into how to like figure out the similarity or the degree of similarity that you can get away with something like this, how far you can push it. If you can get something like degree of difference, like some static number or something, maybe in relation to the Markov decision process or the formulation itself. But yeah, right as of now, no, but that's the kind of thing we're looking into and seeing how, if it makes it easier for us to specify if something can be mapped or not. But yeah, thanks. It's a good idea.
Thank you. So that's a question for the first talk. Thank you very much for the great work. So you introduced the concept of MOMDPs as a formulation that could be applicable to various problems in robotics. Could you talk a bit more about the broader relevance to real-world domains? What other tasks do you envision we could tackle, we could describe with this formalism?
Yeah, I'm thinking about like in the paper, we kind of have the example. I mean, it should be applicable widely to the robotic world. That is the gripper, right? So in the gripper, the pulse of the gripper can be considered to be fully observable because it can kind of measure quite accurately using a sensor of the grippers. But for instance, the object that for instance, the gripper wants to grab something that is unknown, then that one has an uncertainty kind of much bigger than the pulses of the gripper. And that is like an obvious example of applying our method to the gripper. And like gripper is used everywhere, so.
Got it. And another question I had was, you talked about how domain knowledge is basically required to break the problem into high and low level and bottom level. Could you talk to us about how would one go about doing that, or if you have any thoughts about how to make this process smoother? Was that very challenging to get it right? What are your thoughts about that?
Yeah, I mean, that limit is kind of the limit of the hierarchical method that we apply our method on. So if you remember, we apply into there are two ways like the hierarchical isokinetic HAC and the hero algorithm. So they kind of require you to have such domain knowledge, to break into like what should go with the bottom levels, what should go with the top level. But our method can be, it doesn't need to have to be that way, because the bottom level actually can use the same observation from the top levels, like the raw observation, and it should be doing okay in that case. So I don't think that that is like a big kind of limit to our method.
All right, great. So I think we're essentially at time. Unless we have any burning questions at the very last second, I think we can end the technical part of the session here, and I'll pass it on to Dorsa.
All right. Okay, so that concludes the first day of WAFR. Thank you all speakers, respondents, chairs for contributing. So we have an hour and a half, so we can just go to the hotel, hang out, do emails, whatever we're doing in the next hour and a half, or we can just hang out in the bar at the hotel. And then at 6 p.m., we are going to have a reception. The reception is not going to be in this building. It is going to be in a different building. That is the computer science building, the Brandon IRIP building, which is right in front of the hotel. So if you're staying at the hotel, then it's going to be right in front of it at 6 p.m. All right, we'll see you guys there. Tomorrow we'll start at 8:30.